Somewhere, at some point in the history of science, someone made a checklist. It wasn't an official checklist. Nobody published it as a paper or voted on it at a conference. It assembled itself, gradually, from the accumulated assumptions of researchers who had exactly one example of life to study. Us. And who did what any reasonable scientist would do with one data point. They described it, carefully, thoroughly, with great precision. And then, almost without noticing, they started using the description as a definition. The checklist looks something like this. Life requires liquid water. Life requires carbon as its molecular scaffold. Life requires temperatures in a moderate range. Not too hot to denature proteins, not too cold to arrest chemistry. Life requires an energy source, preferably a stable star, at a comfortable distance. Life requires an atmosphere of the right composition. Life requires a planet. Every item on that checklist is true of Earth. That is not a coincidence. It is, in fact, the entire problem. Because when we went looking for life elsewhere, when we built the instruments, designed the missions, selected the targets, we took the checklist with us. We looked for liquid water. We looked for carbon chemistry. We looked for moderate temperatures and stable stars and Earth-like atmospheres. We looked systematically and with enormous sophistication for ourselves. This episode is about what happens when you put the checklist down, not throw it away. The checklist is not wrong. It describes something real, and life that looks like Earth life is genuinely worth looking for. But when you set it aside, even briefly, and ask a different question, not where could life like ours survive, but what does physics actually permit? The universe gets considerably larger. Not just larger, stranger. And stranger, it turns out, is exactly the right word. For example, the many versions of extremophiles living on Earth right now. We, and when I say we, I mean the scientists, those smart folks doing real research, have found organisms on Earth that can survive in environments that were once thought unable to sustain life. These environments, like the intense heat in the volcanic vents 0F, the Mariana Trench, and the acidic environment of the Yellowstone National Park hot springs harbor life. These microbes grow optimally at pH levels below 3.0, and some species can even survive in environments with a pH of 0, like a concentrated acid solution, extreme pressures, and extreme cold. Different organisms have developed varying ways of adapting to these environments. But most scientists acknowledge that it is unlikely that life on Earth originated under such extremes. Breaking the checklist. What extremophiles have already told us. The checklist started breaking down here on Earth, which should have been the first clue. For most of the history of biology, the assumption was that life occupied a relatively narrow band of conditions. Moderate temperatures, neutral pH, standard pressures, the presence of oxygen. Then we started looking in places we had assumed were lifeless, and we found life. A lot of it. The organisms that live in these extreme environments are called extremophiles, a term that reveals, in its very construction, the anthropocentric bias of the person who named them. They are not living in extreme conditions. They are living in their conditions. We are the ones who decided the conditions were extreme. The known physical limits of life, as defined by the hardiest extremophiles we have found on Earth, are genuinely remarkable. Hyperthermophiles, heat-loving organisms, survive at temperatures up to 122 degrees Celsius, well above the boiling point of water at standard pressure. Footnote 1. Gemma barracii, strain 121. Found in hydrothermal vents on the ocean floor, grows optimally at 121 degrees Celsius and can survive brief exposure to 130 degrees Celsius. At the other end of the scale, psychrophiles grow at temperatures as low as minus 15 degrees Celsius in hypersaline environments where the salt concentration depresses the freezing point of water. Planococcus halacryophilus, isolated from Arctic permafrost, grows at minus 15 degrees Celsius with 18% salinity, conditions that would kill virtually every multicellular organism on Earth. Footnote 2. Pressure extremes are equally dramatic. Piezophile thrive at the bottom of the Mariana Trench under hydrostatic pressures of approximately 1,100 bars, about 1,100 times the pressure at sea level. Footnote 3. Radiation-resistant organisms like Deinococcus radiodurans survive doses of ionicing radiation that would be lethal to a human 1,000 times over. Footnote 4. Organisms have been found in the intensely acidic drainage waters of mines at pH values close to zero. Others thrive in soda lakes at pH values above 11. The alkalinity of household bleach. Footnote 1. What extremophiles tell us, collectively, is that the parameter space within which carbon-based, water-dependent life can function is vastly larger than the checklist implied. They push every boundary we thought was fixed. They do not tell us that life can exist without carbon or water. All known extremophiles are still, fundamentally, Earth-type life operating in difficult conditions. But they do something more important than that. They demonstrate, empirically, that our intuitions about where life can exist are systematically too conservative. If our intuitions about Earth-like life in difficult conditions are that wrong, what might our intuitions about genuinely non-Earth-like life be missing? Life finds a way in conditions we were absolutely certain it couldn't. Every time, without exception, one starts to wonder about the exceptions we haven't checked yet. The definition problem, or what are we actually looking for? Before we can ask what physics permits, we need to settle on what we are asking about. And it turns out that defining life, something every human being intuitively recognizes, something that has been the subject of study for millennia, is surprisingly, persistently difficult. NASA's working definition, developed by its exobiology discipline working group and in use since the 1990s, describes life as a self-sustained chemical system capable of Darwinian evolution. Footnote 5. It is probably the most widely cited definition in astrobiology. It is also, as its own authors have acknowledged, imprecise and difficult to implement, a framework for thinking rather than a test you can run. A 2026 analysis of the definition's history noted that it focuses attention on information, molecular mechanisms, and Darwinian evolution through generalization of replication, while remaining deliberately ambiguous about metabolism. Footnote 5. That ambiguity is not an oversight. It is a recognition that the relationship between replication and metabolism in the origin of life is not settled, and that a definition that requires both in a specific form may be eliminating possibilities that physics does not actually rule out. The minimum requirements that most astrobiologists converge on are simpler than the NASA definition suggests, something like a thermodynamic gradient, a mechanism for capturing energy from that gradient, and some form of information storage that allows the system to reproduce and change over time. Footnote 6. Freeman Dyson, in his reflections on the long-term future of the cosmos, argued that the thermodynamic gradient is the only absolute requirement, that as long as there is a difference in energy between two regions that a system can exploit, the basic precondition for complexity exists. Footnote 7. That is a very permissive definition. It does not specify carbon. It does not specify water. It does not specify a planet, a moderate temperature, or a stable star. It specifies a gradient and a mechanism for exploiting it. The universe, it turns out, is full of gradients. Jupiter, the case that Sagan built. In 1976, Carl Sagan and the astrophysicist Edwin Salpeter published a paper in the Astrophysical Journal Supplement series titled Particles, Environments, and Possible Ecologies in the Jovian Atmosphere. Footnote 8. It is one of the most unusual papers in the history of planetary science, a rigorous, mathematically grounded thought experiment about what life might look like on a planet that has no surface. Sagan and Salpeter's starting point was the chemistry of Jupiter's atmosphere. Hydrogen, helium, ammonia, methane, water vapor, and organic compounds whose orange-red coloration in certain atmospheric bands is characteristic of complex carbon chemistry. Also, footnote 8. The energy sources available in Jupiter's atmosphere include solar radiation in the upper cloud layers and the immense electrical discharges of Jovian lightning. Storms estimated to be 1,000 times more powerful than anything on Earth. Footnote 9. The temperature and pressure profile of Jupiter's atmosphere passes through a zone, roughly 50 kilometers below the cloud tops, where conditions are not entirely unlike a dense, high-pressure version of Earth's lower atmosphere. Footnote 8. Within that zone, Sagan and Salpeter proposed 3 categories of hypothetical organism. Sinkers, small microorganism-like entities that drift downward through the atmosphere, reproducing as they fall, returning daughter cells to the habitable zone through convective updrafts, a life cycle analogous to oceanic phytoplankton cycling through a sunlit surface layer. Footnote 9. Floaters, enormous organisms potentially kilometers in radius that maintain buoyancy by pumping dense gases from their interiors and filling themselves with hydrogen. Beings that Sagan later described as kilometers across, enormously larger than the greatest whale that ever was, beings the size of cities. And hunters, faster, more maneuverable organisms that feed on floaters through a process more like absorption than predation, navigating the cloud layers in search of prey. Footnote 9. A 2025 paper extending Sagan and Salpeter's work proposed a 4th category, scavengers, feeding on organic detritus that rains down from higher atmospheric layers, completing an atmospheric ecosystem analogous to the deep ocean benthic communities that feed on material from the sunlit surface. Footnote 10. None of this is evidence that Jovian life exists. Sagan was careful about that. The paper is an exercise in possibility, not discovery. What it demonstrates is that the specific combination of energy source, chemistry, and physical structure required for a self-sustaining biological system is not obviously absent from Jupiter's atmosphere. The checklist that rules Jupiter out is an Earth checklist. A checklist written from first principles about what life requires: thermodynamic gradient, energy source, chemical complexity, mechanism for reproduction, does not automatically exclude it. The Juno spacecraft, currently in extended mission around Jupiter, has been characterizing the planet's atmospheric chemistry and dynamics since 2016. Footnote 11. It was not designed as a life detection mission, but the data it is generating on the distribution of water, ammonia, and organic compounds in the atmosphere is the foundation any future targeted search would build on. The outer limits, neutron stars, and the edge of chemistry. Now we go somewhere genuinely strange. In 1973, radio astronomer Frank Drake, the same Frank Drake who wrote the equation, the same Frank Drake who spent his career listening for signals, proposed that the atomic nuclei inside neutron stars might support a form of nuclear chemistry. Footnote 12. A neutron star is what remains after a massive star exhausts its fuel and collapses. It packs roughly 1.4 times the mass of our Sun into a sphere approximately 20 kilometers across. The density is almost incomprehensible. A teaspoon of neutron star material would weigh about 10 million tons. The surface gravity is approximately 200 billion times that of Earth. The magnetic field is 1 trillion times stronger than Earth's. Temperatures on the surface reach millions of degrees in a young neutron star, cooling to perhaps 1 million degrees over tens of thousands of years. Footnote 13. No molecule, as we understand the word, can exist under these conditions. Electrons are stripped from atoms. Conventional chemistry, the chemistry of electrons forming bonds between atoms, is impossible. The checklist does not just fail here. It vaporizes. But Drake's observation was this: protons and neutrons inside an atomic nucleus are themselves arranged in shells, analogous to the electron shells that govern conventional chemistry. The variety of possible nuclear configurations and the extraordinary density conditions of a neutron star crust is enormous. If those configurations could combine into structures of sufficient complexity, supernuclei, Drake called them, analogous to the molecules that serve as the basis of life on Earth, they might in principle support something analogous to information storage and reproduction. Life of this type, if it existed, would operate at the speed of nuclear reactions rather than chemical reactions, a timescale roughly 1 trillion times faster than Earth biochemistry. Drake described with deliberate humor the perspective of a hypothetical scientist on a neutron star encountering the concept of atoms for the first time. Strange exotic objects, unimaginably large, moving at glacial speed, building up into structures that somehow persist for billions of years. Footnote 12. A 2020 paper by physicists Luis Ankardoki and Eugene Shudnovsky at the City University of New York examined the question more formally: whether self-replicating species could flourish in the interior of a star, using not nuclear chemistry, but cosmic strings and magnetic monopoles as the information-carrying medium. Footnote 14. The paper is, in its author's own description, wild and speculative. It is also a serious attempt to ask whether the thermodynamic gradient and information storage requirements for life can be met by physics other than atomic chemistry. The honest answer is, we do not know. We cannot rule it out on physical grounds. We have no way to detect it if it exists, no instrument sensitive to nuclear-scale chemistry at stellar densities, no signal to listen for. It is speculation at the edge of what physics permits, held in honest uncertainty. But here is what that honest uncertainty implies. If life can potentially exist across a range from -15 degrees Celsius hypersaline Arctic permafrost to the surface of a neutron star, even in principle, even theoretically, then the parameter space within which something meeting the minimum definition of life can operate spans essentially the entire observable range of physical conditions in the universe. Not every environment, not most environments, but an extraordinary, almost dizzying variety of them. What this means for the search and for the sub-series. Let me bring this back to where the sub-series started. Episode 1 asked whether carbon was the only scaffold for life. The answer was probably not, under different conditions, but the evidence for alternatives remains indirect. Episode 2 asked whether intelligent life sealed inside ocean worlds could ever signal us. The answer was probably not, because the path from intelligence to radio requires fire, and oceans don't permit fire. Episode 3 asked whether our search methodology was looking for the right thing. The answer was probably not entirely, because the methodology assumes our technological trajectory. This episode asks the deepest version of the same question. Is the life we are looking for the only kind of life physics permits? And the answer, from extremophiles to Jovian atmospheres to neutron star nuclear chemistry, is almost certainly not. The sub-series' central argument has been that we are the measuring instrument. Everything we know about life is one data point. The bias runs deep into our definitions, our instruments, our search methodologies, our intuitions about what counts as a habitable environment. This episode shows that the bias runs all the way down to the physics. Not because the physics is wrong, but because the physics we applied was always Earth physics, expanded cautiously outward from one example. The NASA definition, life as a self-sustained chemical system capable of Darwinian evolution, is an attempt to step back from the Earth checklist. It is deliberately agnostic about carbon, water, temperature, and pressure. It asks only for a system that can sustain itself and change over time. That definition, applied honestly, does not rule out sinkers and floaters in Jupiter's cloud layers. It does not definitively rule out nuclear chemistry at neutron star densities. It does not rule out the extremophile living at 121 degrees Celsius in a hydrothermal vent, which we would have called impossible 50 years ago. What it rules out is much smaller than the checklist implies, and the universe is much larger than the checklist suggests. So here's where 4 episodes have brought us. Life might be hiding under kilometers of ice in ocean worlds next door, sealed away from any technology that could signal us, intelligent by any reasonable definition, permanently unreachable by the search methodology we built. Our search methodology might be looking for ourselves, radio signals, megastructures, the technological residue of a civilization that followed our specific path. The chemistry of life might extend well beyond carbon under conditions we would never have predicted from Earth biology alone. And the minimum physical requirements for something that qualifies as life may be met across a range of environments so vast that ruling anything out becomes almost philosophically difficult. None of this means the universe is teeming with life. The Fermi paradox remains. The silence remains. The arithmetic of temporal overlap that the channel's first episode laid out remains genuinely sobering. But it does mean that the universe we are searching is larger than the universe we built our instruments to find, and that the life we might be missing is not hiding because it is rare. It might be hiding because it is different. The sub-series asked, what if life doesn't look like us? For episodes later, the honest answer is, it probably doesn't. And we're only just beginning to build the tools to look for it anyway. It's a Tuesday. Somewhere in the Milky Way, something is exploiting a thermodynamic gradient in conditions we would have called impossible. It is doing so without caring whether we would recognize it. The universe does not require our recognition to proceed. There's still a lot of it left to look at.